Okay, it is time. Come on in, come on in. We're peddling only slightly used programming paradigms here. They've got about 20 years on them, but or more, but they're still good as new. Come and have a nice seat, preferably up front, if I can keep an eye on you. Okay. I've got absolutely no slides today. As you can see, the only thing open is Visual Studio. I have Functional Journey 1 and Functional Journey 2, and that's where we'll spend the next hour. I'm Matt Torgersen. I design C# for a living. And yesterday I told you all my secrets about what might happen. So there'll be absolutely nothing new today. Okay. There might be things that are new to you or new ways of thinking about it. But other than that, you know, this is a trip down memory lane. You can lean back and just rest in the knowledge that this has already happened. There's nothing we can change here. So C# started out as a very typical object-oriented programming language for its time, as you know, has evolved a lot ever since, and not all of that evolution, but a lot of it has been inspired by functional programming. So there was object-oriented programming and functional programming back then, and they were largely separate. There were a few early valiant attempts to unify the two paradigms. Scala is an early example of that, trying to take these seemingly opposite concepts and bringing them together. C# started out way in one corner, and we found that a lot of the functional stuff has been a good supplement and helps kind of make the language sort of give you a full range of options. And so we tried again and again to take functional concepts and integrate them as well as we can into C#, trying to make them not stick out and feel like a foreign element, but merge them as well as we can with what's already there and the sort of core object-oriented feel of it. So what I'll do today is just take you on a journey, starting with C#1, and then we'll just see how far we get within the hour, and talk about each of the functional concepts and how it relates to the object-oriented counterparts and how we integrate them in the language along the way. So it's also maybe a bit of a refresher course if you had a functional programming course in university or something. Or if you're working in a functional programming language today, it's a chance to be snarky and say, you call that functional programming? So whatever floats your boat, there are many ways you can take this. And feel free to ask questions along the way, and we'll get as far as we can. So this is more or less pure C#1 that I have here on the screen. I don't like that my code kind of doesn't fit on the screen for a demo. So we're going to just start out by cheating and using some newer language features that don't have much to do with functional programming, so I don't feel bad about it. But I want to just use top-level statements, C# in demo mode, essentially. Oh, that's not where I go. I go to the main method, and I'm just going to use a refactoring for it. Convert to top-level statements. So there you go. It's top-level statements, and there are some local functions as well, and they didn't exist until much later. Don't worry about it. Okay. So functional programming at the very, very core, if you were to say one thing that is the core engine of functional programming, it's first-class functions. It's the fact that functions can be values, and they can be passed to other functions that can invoke them. And a function that takes another function is a higher order function. And that's how you do your abstraction. That's a core abstraction mechanism that makes everything else tick. It goes all the way back to the lambda calculus, which is a mathematical model that was invented before we even had physical computers to run things on. And the core lambda calculus in its simplest form really has only one thing in it, and that's functions that take other functions, call other functions, return other functions, and that's all there is. And that's really the core bread and butter inside of functional programming. And most object-oriented programming languages at the time did not have a notion of first-class functions. You could still you can still, so I have here some code that takes a predicate, right? So I'm taking in another function that I can use, that I can call to get a result that I can then, that depends on what function was passed in. Like if you were in a language like Java, for instance, you would probably have an interface, interface iPredicate, and it would have a single, it would have a bool do int I method or something like that, right? So you can fake first-class functions with objects by having a shared interface saying, here's a thing that has a function that has a method inside of it, and you can pass the thing around and then call the method, and that's like having a first-class function. But you kind of have to emulate it, and it's extra work and so on. And so one of the few functional-ish-esque things in C# from the outset is delegate types. Delegate types are a form of function types, and they allow you to pass functions around first class. It's a pretty primitive thing. It's not like, it does not look like any respectable functional programming language, but it's there. Delegate types are these type declarations you make. They're named types, just like classes. So there's no anonymous function types that you can just mention on the fly. You have to create one. There's all kinds of ugliness about delegates that I'm barely even going to talk about. They're also a collection type for some reason. There could be multiple functions inside of a delegate, and it's just, that's all some nastiness that somebody just asked me before the talk if I had a time machine, could go back, and that would be one of the things I would change. But anyway, but I can use the delegate here for my filter function, and I can let's see, p here. I can call p here as a method call, as a function call. When I pass it, I have to pass it by name. I have to have a named method somewhere, and then I pass that method by name. So I have to declare the function as well as something named. I don't just have anonymous function values at this point. But it's a good start. And we'll leave that first-class function thing there for a bit as we go and talk about C#2. So the really big thing that happened in C#2 was generics. C#1 did not have generics. You see me using array list here, and that really gets us into talking about polymorphism. There's sort of several kinds of polymorphism floating around. Polymorphism is Greek, and it means something like many forms or something like that, many shapes. And polymorphism is really about how am I able to write code that applies to multiple different types. Okay? And object-oriented programming and functional programming take very different approaches to this in their outset. Object-oriented programming is all about subtype polymorphism, where we say everything's an object, and there's a whole hierarchy of ISA all the way up. And if you pick yourself a type up there, then everything else in the hierarchy underneath it can be substituted in. So in the case of array list, that has an implied element type of object, and we can put everything into an array list. You can have, in the same array list, you can have all kinds of objects, just all together in there. So that's subtype polymorphism. It's about everything. Then there's parametric polymorphism, which is a very functional concept, and every strongly typed functional programming language has that as a core concept, where a type can be a function too, right? And you can say something like, I'm a list, but I take a parameter, and that's a type parameter. So I can be a list of, in this case, int. And then the list type is no longer a list of everything. It's a list of anything. But you have to say which of the anythings it is a list of. Right? So it's a different kind of polymorphism that lets you be specific, but it still enables you to write code that applies to everything. That's really, and we go and add this other kind of polymorphism to C# and many other object-oriented programming languages do this as well, because it's really annoying to have a list of everything. When I know I'm only going to put ints in there, but the compiler doesn't know. It's like, hey, there might be like pigs and cars and whatnot in there too. So just to be on the safe side, when things come back out, we're going to make you, cast them back to int, that you perfectly well knew that was already in there. Parametric polymorphism, on the other hand, lets you say what's in there. And so as soon as I get my code up and working here again, I no longer have to cast things when they come back out because I already know that they're int. I have a strongly typed collection type instead of a weakly typed one. Great. And of course, generics really, really change the face of C# programming forever. It's a big deal. But that's like the first major import from functional programming languages, unless you count delegates as the first. So really important here. And it's not just that, I can get rid of a cast, whoop-de-doo. But it also means because the list of int is now a strongly typed collection type, I can have strongly typed helper methods on that type, right? I can use, in object-oriented fashion, it can offer a bunch of methods, but in sort of functional fashion, they can be strongly typed along with the element type of the collection itself. So instead of actually creating my own array here, using these two lines to allocate an array and fill things into it so that things are strongly typed, I can just return dst.toArray, and call that strongly typed helper function and have it create the array for me. And now I can just delete. These. What? These two lines of code here. Hang on. Fat fingers. There we go. Right. So great improvement. And it also means that we can. It means that array is no longer the only strongly typed collection type in the language. So instead of using arrays as interchange types, which is all kinds of bad, right? Who knows? How do you even do that safely? You're passing someone an array. Well, they can't trust that you aren't changing it on them while they're looking at it, and you can't trust that they aren't changing it while they're looking at it. And so you either have to do the defensive copying or all kinds of stuff. It's not a good exchange type for many things. But now we could use other exchange type. We could use list of t, which is also mutable. We could also just abstract away for just the things we need and use, for instance, iknowable of int here. Okay. And now we could return that as well, and then let's return that. And now we get a complaint from up here that this is no longer an array. Well, that's fine. We can just do that as well, because iknowables are things that can be for each, and everything's hunky-dory. Okay? So, but of course, not only can we consume generics, we can also write our own generic things. Yay. So let's start with, predicate here. We can have our own generic types. So predicates should really be predicates of anything, right? So I could make it predicate of t and say t here instead, and then use predicate of int up here. And now, I'm reusing my generic type across potentially across many different types. I can also have generic methods. So we could make the filter method itself generic and say it's actually not just filtering for ints, it's filtering for t's. And now I have to go and write t a bunch of places. I just had coffee, so a little t will be fine. Okay. There's probably, hey, Copilot, please replace all the right ints for t's here. Okay, there we go. And all of a sudden, we have that same functionality work for anything, rather, not for everything. Right? And so we can generify our own things. You notice that I should really be saying filter of int up here, passing that type argument to the type parameter. But another thing, like functional languages that are strongly typed often lean into a lot, is type inference. It's like, okay, there's a lot of types going on here. The types in functional languages tend to get very large, partly because they don't have subtyping and those things. So if you look at the types, they can be sort of a little overwhelming. And so generally, these languages do a lot to keep the types to themselves and not have you say them or look at them as much as possible. And so they do very aggressive type inference. Now, in an object-oriented language with subtyping, we can't do as much type inference because there's less we can know when we look at a person. We can't know if it's a student or teacher or whatnot. So we can't be as precise in type inference, but we also may not want to. It sort of feels like the cautious and right thing to do at this point in C#'s evolution, to be cautious about how much type inference we do, so that it's kind of local and that it doesn't surprise you and it doesn't depend on things that are too far flung. Like if you're in my talk yesterday, I talked about spooky action at a distance. Like you change something up here and then the type down here becomes a different one, which means we pick a different overload over here, which means that the thing that's returned down here is empty. Okay, let me debug that, right? So we try to be generally still very explicit with types, but we do like ourselves a little bit of type inference. So you don't have to say the types so often, especially because the types now tend to be bigger because they will have type arguments. And some of those type arguments will have type arguments. And before you know it, you have a lot of angle brackets. So we do that, like we do type inference just for type arguments for generic methods, not for generic types. And we also do like very simple, just var here that you can sort of, not really type inference, right? It's just looking at, hey, does the thing on the right-hand side have a type? Well, let's pick that one. It's not rocket science here. So var as well. And I'm cheating a little here because var actually only comes in C#3, but I was talking about type inference. You get it now, without extra cost. Oh, I couldn't do that because the way I'm creating the array is array specific. Okay, no, I can't do that. I can't cheat either. Okay, let's just keep the array type. Okay, there we go. All right, with me? So there are a few other things that we steal from functional programming at this time beyond generics. Generics is really the big one, but there are a couple other things. There's this notion of generators where you have a function that generates elements along the way that sort of kind of comes from functional programming. And the idea really is, and we can watch it here in the filter method, that instead of creating an array and sending it back, I could really just yield out the elements one by one as I create them with the beautiful yield return syntax that we landed on for breaking change purposes. Yay! And now this, because of the presence of yield return, this method becomes a generator, and it actually wants you to not return anything explicitly because the compiler is going to take care of generating a suitable class that implements IEnumerable and implementing it in such a way that this code runs a step further every time you ask for the next element, right? So it's kind of lazily running the code inside. As soon as you yielded something, it's just going to sit here for a bit, waiting until the next time the for each up here comes around and say, okay, give me another one. And it'll be like, yay, they want me to help out again. And they call the predicate on the next thing, and they keep going lazily, right? And you have functional languages like Haskell that are lazy at heart. Like the way that they do the whole evaluation strategy is you only call things at the very last moment when you're absolutely sure that you're going to need them. So that kind of references back to that a little bit as well. All right. And I want to show one more thing. We talked about first-class functions, and while we sort of embrace classes or functions as first-class values already in C#1, we didn't really let you write anonymous function. You can't just write an expression that's a function. And in C#2, we're like, we're gonna fix that. We're gonna have a great syntax for writing a function in line as just an expression. And that great syntax is going to be not lambda expressions. Okay, so we have this little intermediate thing that we thought was going to be good enough in C#2, where you put the delegate keyword, anonymous methods, we call it, and then you take the thing that the rest of the method essentially and put it there with the parameters and a body. And it's an anonymous function. You don't have to have this declaration anymore. So our code got a little shorter again. That's very nice. And we're going to come back to that in just a minute. So, what's that? Don't need line 9 either. Oh, you're right. Thank you. Thank you. Good catch. Good catch. Yeah. Anyone else want to play co-pilot? Yes. So he's pointing out that using IEnumable as the exchange type here, while it protects against much mutation, also has a pitfall, because it can be, you could get like, just like we're producing IEnumerables that are lazily evaluated here, you could get one of those as well. And that means that if you iterate them multiple times, well, everything gets evaluated multiple times, right? So there's a cost to this lazy kind of IEnumerable that you just have to be aware of. Now all of a sudden you have to think, is my thing already realized and I'm just kind of going over the results, or am I realizing it every time I go over it? And if you think that's bad now, well, hold my beer, right? Because now we're going to C#3, where we really lean into this like big time. So thanks for. Yes, many developers still don't realize that. One of the things that, but let's get to that when we've shown, when we've gotten to queries. Right? I mean, this is, this will become obvious in a moment. For now, let's just say, okay, in C#3, we're like, we want to slay querying once and for all. And functional programming has a whole toolbox of things that you can use to make querying a really good experience. Okay, so databases, they're all the rage, they're the future, and we want to do better with them. Like object-oriented programming and databases have been at odds, lots of impedance mismatch. We want to fix that or make it a lot better here, and that's a whole mission, like up and down the stack, including a lot of stuff in the language. So we go to town, and we're going to need a lot of first-class functions and stuff here. So let's start by doing better on the anonymous functions. Okay, it was a thing, but it wasn't good enough. This does not feel first class. Like this is a very clunky thing to have in the middle of your expression. Can we do better just syntactically? And yes, we can. And again, inspired by functional programming and that lambda calculus I mentioned up front, we now have what we call lambda expressions. It's sufficiently cryptic. It almost sounds like a brand name of sorts, but it's really just like another name for function literals, function expressions. So we could do this, like we get rid of that big keyword and put an arrow in again. Okay, I guess that's all right. But another thing that you find in functional programming languages is that they're often very expression-oriented. Because they have less imperative programming, they don't need statements so much. You're not really changing things. And so most things are just expressions. Some functional languages don't have a notion of statements. It's all just expressions. And so when you have just a single return statement, well, maybe you should be able to just put an expression instead, right? So just put that and have an expression body in your lambda instead. And things got a lot more terse and nice all of a sudden. And oh, by the way, we're passing this to a predicate of int. How do we know it's a predicate of int? Well, that's because we are calling filter of int. Well, how do we know we're calling filter of int? Well, that's because we passed an array of int. Okay, good. So type inference can go through and figure out what kind of function we are supposed to pass here. And it knows that we're supposed to pass something that has an int parameter. Why do we have to say that again then? Well, and then you don't, right? You can just infer from context the parameter type of a lambda. And when you have only one You can even remove the parentheses and everything gets super nice. It's almost like Squint and you have functional programming. Now you can really implement, you can do lambda calculus stuff now in C#. It's beautiful and elegant and very weird and mind-bending. So I'm not going to do that. Okay, so far so good. This is nice and functional, but what if I want to, querying, I'm going to probably do more than just filter once, right? I'm going to call multiple. Okay, so let's say filter is like it's a query method of sorts, but I'm probably going to want to apply multiple different ones or same ones. I'm not going to write other ones here, but let's say I want to filter the output of filter. Now we get to a thing that's not so nice in kind of functional notation here. Let's say I want to filter the output and pass it a lambda to say, I only want the even ones. I modulo 2 is 0. I can do that, but now code becomes hard to read, right? You start in the middle with an array, and then you wrap it in the first filtering, and then you wrap all of that in the next filtering. You have stuff both before and after the thing that kind of belongs together. So this code doesn't flow very well. And functional languages have addressed this long ago with an alternative function call syntax that is pipelining. Okay, so instead of I'm going to cheat and lie a little bit here, but the general premise holds true. Instead of having slapping function calls around, you're going to pipe things through like a chain of functions from left to right. And the way that might look if we were doing that in C#, which we aren't, is let's say that I take the result of this first filter, and instead of slapping filter around it, I take the outcome from it, and let's abuse the shift operator here. I pipe it into another call to filter, like that. But a call where the first argument has been omitted, because that's already coming in on the pipe. Right? And you could even imagine doing that twice, right? We could actually start with the array, and then we can pipe it in to a call to filter the first time as well. And all of a sudden, the code flows really nicely, apart from the fact that you get red squiggles because this doesn't actually exist in C#. But we want to get that kind of fluent, as it has come to be called, that kind of fluent style of invocation. So this is a place where we have to get a little more creative, because we want to get that, but we also want it to feel more object-oriented. And we actually like the discoverability of when you say dot, you know what your options are. So this is where we come up with extension methods. Okay, so we want to take this filter method and we want to make it an extension method. So bear with me for a bit as I create a static class. Let's call it. That's because I have the filter method there first. I can do this. Public. I wish there was a refactoring for this, but I would be the only one ever using it. Public static class extensions. Open curly. Close curly. Okay, we get in there. Now this guy needs to be public and static as well. And what's wrong with it? Oh, accessibility predicate down here needs to be public as well. Okay, back in green. And now the new language feature is you can put a special modifier on the first parameter of your static method, and it is now an extension method. It is supposed to be able to pretend that it's an instance method on its first argument. And with that, we can now go and say dot filter, right? So you can see how this is pipelining in its own way. It's pipelining that the function has to anticipate that it's going to be pipelined, right? So it's not as free and ever present as pipelining in functional programming. But on the other hand, what you win is that when you press dot, you can see all the extension methods as well. So you get this in the IDE and the tooling, you can get this like strong assistance with what are my options right here, and you get these contextual members essentially that only exist if you're in a context where they make sense. And as you talked about yesterday, like extension methods have become a runaway hit in terms of just software composition, and we're now trying to come up with a way of generalizing them to extension properties and statics and operators and all kinds of things. Okay, so very nice and fluent there. It should look more like SQL, so let's call it where instead of filter. And actually, we're going to make a library of these guys, these extension methods. So I'm actually, and literally, this was the implementation of the first where method. We made it a little more efficient since then, but logically, this is what the where extension method looked like in the query libraries that we built. And now you can also say select and join and all kinds of SQL-y stuff as functions here. Now, this is really cool if you want to query in-memory data. It's cool syntactically, at least. Some will say it's not the most efficient way of doing it, partly because of the lazy evaluation, and which in and of itself adds overhead, and then you might accidentally do it twice, and it adds twice as much overhead. So there's some unpredictability. It's hard to kind of look at code and predict its performance characteristics. I think that's something that we weren't as aware of back then. In our defense, neither were the functional programming languages. But we really want to query, external data, really just SQL, but hey, let's make a general mechanism for it. And to query external data, we need to do something smarter. We can't just we don't want to, call a SQL database for every single where method and sort of say, hey, can you filter with this? And now can you filter with this? And now can you filter with this? That's very chatty and very expensive. And we could download all the data and do it locally and lose every benefit from having a query database. So what to do? But what we really want to do is we want to take the whole query and kind of bundle it up and send it off to the database as a SQL query. How can we do that? Well, we use another thing that is a functional staple, which is code quotation. Right? We code as data. There's what's arguably the oldest actual functional programming language, Lisp. It leans into this very heavily. Like code and data looks exactly the same. It's all parens and identifiers, and that's pretty much all there is in the whole language, right? And so code will be something in parens with some identifiers and some more parens, and data will be something in parens with, that's just what everything looks like. And it means that you can very easily quote some code, and all of a sudden it's just a data structure. And this code quotation means we can get code as a value at runtime. The code itself is an inspectable data structure. Can we do that? If we can do that here as well, we can do some nifty tricks. And so code quotation in the form of expression trees becomes a thing in C#3. So the way we do it is if array was actually a SQL database, it would implement an interface called iQueryable. That's like IEnumerable, but for things that need to quote the query expressions. And it's not, but I can pretend it is here by just saying asQueryable. There's a method for that. And if we turn our array into a queryable and we look at the where method, we can see that it has changed its signature now. We get overload resolution gives us a different where method that does not, can I point in here without it going away? I can. Instead of taking a func of incommensurable, I forgot to tell you about func. Let's get there. It's just like the next level. C#3, we take the next level of generalization of delegate types, and we just have func of action and get closer to you not having to ever declare them. You can just use the ones we have in our library aside. But so there's a delegate type inside here, but it's an expression of that delegate type. And when the compiler sees expression of something, it says, aha, they don't actually want a delegate. They don't want a first-class function. They want a first-class syntax tree of a function. And so instead of compiling this into code, they compile it into a data structure, or rather code that generates a data structure that resembles the structure of the Lambda itself. Okay? And so the where method gets a little syntax tree of your Lambda. And then it says, instead of doing something, starting executing on that, it says, hey, based on that, let me quote myself. Let me give you a little where call that's a syntax tree, and then I stitch in the one I got, and I have a where call, and put that into another iQueryable, and then the next where call takes that and says, let me stitch that, and so all of these where calls, they combine to build up a big syntax tree of the whole query and stick it inside the thing that's returned here, the iQueryable that's returned. And then the magic happens when you for each it down here. It'll go and say, hey, I should ask what provider I belong to, like where I started, where the array came from to begin with. I should ask it to do this query for me. And what the SQL provider will do is to say, okay, I've got a whole query here. Let me translate that to SQL right now as one big query. Just at runtime, in the middle of everything, just translate that to a query, send it over, get the results back, and start yielding those out to the user as part of this for each. Okay? It's a lot, but it works. And it's pretty cool. And Entity Framework to this day, I guess, is a big part of how that whole thing works. So it had a lot of staying power too. All right? Querying doesn't quite look like SQL yet. Wouldn't it be cool if we just had SQL in C#? That's gonna be the marquee feature. We're gonna have this beautiful SQL syntax, and every SQL developer will flock to C#. And so we come up with a syntactic sugar over these method calls here, that is query expressions. So you can say, from I in this thing, where, as a keyword, where, and then the I kind of gets reused down here. You can see how we do the syntactic transformation. Where another thing, okay? And again, the lambdas go away, but it translates into exactly the same thing, lambdas and all, underneath. And it's going to insist that we end with a select clause, because SQL. Unlike SQL, though, we don't start with a select clause, we end with it. Because if you start by selecting something, how do you know what you have to choose from, right? So from a programming language perspective, it's better to have the things that introduce the variables before the things that consume the variables. So we did flip that around. And you have much more freedom compared to SQL in terms of which query clauses you have in which order and so on. But it's familiar. It's familiar. Okay? So C#3, all about querying, lots and lots of functional stuff. You tired yet? Okay. Well, let's go for more. C#4, okay, so actually now we get to a bit of a dead zone in the continuum of time in terms of functional stuff. Like we feel like we've exhausted our functional plunder now for a bit. C#4, we're all about dynamic. It was the whole thing, we wanted Python and Ruby on .NET as well, and it should all like be one happy family calling across JavaScript, you name it. Came up with this great big thing that lets you be super dynamic, but has nothing to do with functional programming. So luckily, I get to skip it. C#5. At this point, F# has a really cool, comes out with a really cool implementation of async that is super inspiring to us. And they use what's called monads, and really queries are, this is a very query-specific syntax for it, but the way we do queries in C# really is also monads. It's just tailored specifically to query, but monads are an abstraction mechanism that lets you do a lot of things where you have a flow of code that you want to somehow abstract over the whole flow and do things behind the scenes. So F# has this general purpose feature for that. It's called workflows, I think. And they do async with that as well as other things. And we're like, ooh, async, because now the cloud, back when we did this stuff, the cloud wasn't really much of a thing. It's just coming. But now the cloud, we need to do a bunch of distributed programming essentially, and you need to be able to deal with asynchrony. And doing that without language support sucks. So we look very hard at what F# does. We decide that it simply is not a good fit for an imperative programming language, and so we do something else instead. And so we're not going to talk about async much in here today, because the way we chose to solve it was materially different from what F# did. But it was still a big inspiration for us in like having async be integrated into your code flow. So I still want to mention it. Instead, I want to go to C#6. We didn't do much in C#6, and I'm going to switch to a different demo here. We didn't do much in C#6 because we were busy building our own compiler again, but this time in C#. And so they said, can you please not add too many language features for a bit? And that was fateful, because Anders and I were like, but that's what we do. We add language features. What do you want us to do? And we went over and did TypeScript instead. So, and then they said, okay, we're ready. And I came back and Anders stayed. And that's why I'm up here today and not him. So take that, Anders. But of course, there are more things to learn from functional programming. And they also have to do with the cloud, the next chapter we get into here. Let's see, we have 20 minutes left. OK. So object-oriented programming, great. We encapsulate data and functionality together strongly. And like, for instance, when you have functionality that's sort of shape-dependent, right? You want it. It's logically the same thing, but it behaves differently in the specifics depending on what type it's for. We do that with virtual methods. So I'm having this render method here, and it's virtual over my hierarchy of 2 types, but demo. And I just override and do something different, but it's logically the same function. And that's how I make something that behaves dependent on a shape, but is really the same function. That becomes a problem in the cloud, because you see a vast separation of data and functionality. Data becomes long-lived, the shape of data becomes long-lived, and it becomes detached from what it's being used for. There might be a few key things that you always want to do with that data, but by and large, you'll have many different apps or services or whatnot using the same data. And they also want to have shape-dependent behavior, but they can't all become virtual methods on the data itself, right? They can't all like go in there and put in their own virtual methods. So there's a separation of concerns that needs to happen here. And functional languages, they were on the right side of history with this one, again. And so so it's time to go stealing again. And so let's try to look at, if we wanted to do it the functional way using the tools we had at the time, what that would look like. So instead of having a virtual method here, instead of calling mads.render here, we would say render mads. Okay, so it would be a function. Render would be a single function, and let's write that function. And that function itself has, string render. That function itself then has type-dependent behavior built into it. So render person p. And how should we implement that? Well, it'll have to be a bunch of like if-then logic. So let's see if we can do it as an expression-bodied member, because hang on, expressions are cool, right? So not only lambdas at this time, but other functions as well should be able to be expression-bodied. In fact, these guys down here could be expression-bodied as well. That's another like little inspiration. But beside that, let's start with just doing the person stuff. We should, like all else equal, we should do what a person does here. So to start with, let's do that. But really, we want to first check, is it that other kind? But before we do that, we notice we got red squiggles here because we don't have privileged access to the data anymore. We are outside of the type. We need to restrict ourselves to only public data now. So this separation of concerns means that you are no longer encapsulating with the data, and that means you're limited to public data only. So it's a lot more like decapsulation, decapitation. Okay, so, but we can do that. We can dot in, that's fine. But now we want to say, okay, we have all these many derived classes. I only have one, but that's, you get the idea. So we have to first ask, is this thing really, if P is a student, then do the student thing, otherwise do the person thing. I'm going to take this, the student thing. We're just going to do the same thing, right? We're just going to put it in there and make it go through the public thing. P dot first name, great. P dot last name, great. P dot ID. I'm getting the hang of this, no sweat. Well, oops, hang on, right? I need the colon here as well. But there's still a squiggle left because person doesn't have an ID. This is cumbersome. How do functional programmers live? Well, they have pattern matching. And this is where we add pattern matching to C# as the alternative to virtual methods to get shape-dependent behavior. So we start small. We introduce this new thing called a pattern. A pattern is essentially a thing that is both a predicate, like it checks whether something is true, but when that something is true, it is also an extractor. It can extract data when the predicate part was true. And that's a really powerful abstraction. So the one pattern is student S here is a new pattern, which says, if you're a student, let's extract you as a student. And now we have a stronger type variable for the same thing. It's the same object as P, but because we checked that it was a student, we can use it over here and actually access the ID. Right? So pattern matching, great. And now we can go and get rid of our virtual methods down here. And this is now the way that we do our shape-dependent behavior. And now we can go and have independently implemented shape-dependent behavior in multiple different apps and services and all over the place. Great. Still a little clunky. You can also use, so in C#, I think we're in 7 at this point, you can use patterns in is expressions and in switch statements, but switch statements are from hell, right? Nobody wants to write those. So in C#8, we do switch expressions, which are like the cool cousin of switch statements. So the way you do that is you say switch, you say P switch, and then a switch body that is going to take us a little, like a minute or two before the squiggles go away. So essentially what you do is you put cases in a switch and they start with a pattern, and then they have that fat arrow that we know from lambdas, and then they have an expression that is the result we want if it's a student. And that's just the thing down here, right? That's just this. Comma. And then the next one is sort of like, we can just say that's the default case. So it's similar to having an if-then or a conditional structure in many ways, but it's stronger. First of all, it's more readable, right? You can read the cases, dung, 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 dung. It's like the Fluent. It just makes, it's good for readability. And it's in the order that it happens. And when you get one that catches, you're good. But it also has, beyond like being less confusing code, like no more nested if then else's, it also has stronger checking. Let's say we didn't do that last part. It's going to give us a warning saying, hey, you're not handling all the possible values. You're only handling the student ones. Would you like to handle the rest? Or would you like me to throw you an exception? I'll handle the rest, thank you very much. And also, like if I swap these two, it'll say, in a sterner voice this time, with a red squiggle, it'll be like, hey, you can't ever get here. That's wrong. And that way it helps you kind of keep your logic clean and avoid kind of over time through maintenance and whatnot, kind of having that decay of your conditional logic that we all know so well. So that's really cool. But we also, so really a big step forward with the switch expressions, but also we add more and more patterns to C#, C#8, C#9. We keep adding more kinds of patterns. Let's say, so there's really a little bug in here, right? Because what if the first name is empty? And I'm taking the first letter of it, like that's going to throw. Well, why don't we deal with that case? So we can deal with it in multiple ways. We can actually add like a Boolean condition. We can say underscore when p dot first name dot length equals 0 or something like that, right? We could do that. But we can also use recursive patterns, which are patterns that look at a value, sort of deconstruct it and look at its parts, right? So there's an object pattern, for instance, here. We can say if the thing that comes in, if the person that comes in has a first name for which this following pattern applies. So if it has a first name where that is the empty string, for instance, a constant pattern, then we'll just output, the last name, Peter last name, say, okay? Or we could say, looking forward to list patterns, which will be in a later version, we can say if it's the empty list of characters, let's do that. Or we can say if it's, what's that? If it's is null or empty, we could use the when clause again to say is null or empty. Or we could also do that as a pattern because we also at this point have introduced combination of patterns. So you can say if it's null or the empty string like that, right? Or we could say if first name dot, we can actually apply recursive patterns inside a recursive pattern. We'd say if first name is a thing where the length is the constant 0. There's so many ways of recombining these recursive patterns. And just pick whichever one makes sense for you. And if you go too crazy, people will tell you in code review. So, because it can get pretty gnarly, but you can also just kind of stop while it's good, right? So, pattern matching, a thing that we've leaned into a lot, and people use it a lot, and it's really cleaning up a lot of code, especially when virtual methods just aren't the right thing for you. So, the last thing I want to talk about is immutability, and again, we're sort of at a core difference between sort of the pure object-oriented and the pure functional paradigm. Pure object-oriented programming is imperative in nature. Objects have state, and their state evolves over time as you mutate them. Okay? That's just how we model the world. Functional programming is more mathematical. It's about values. And by default, you don't have mutable state. A value is a value is a value. So what you want to model is really not like the object. There won't be like a single thing in there that models me. There will be maybe even a set of different records, different values that represent snapshots of my state at any given time. That's a really powerful way of programming because of a number of reasons. One is parallelism. If you don't have mutable state, you don't have shared mutable state, and you don't have to have all these locking things that will always go wrong all over the place. And undo is great because you can keep the previous state and you can just revert to it and it's still there, like it wasn't destroyed in a destructive mutation. So how does this all work? Like, let's look at me and let's say, so I actually used to be, before I got married, I used to have a different last name. So let's say that somebody nefarious tries to change it back. Match that last name equals Nilsson is what I used to be called. Okay, bad. I don't want that to change. I want to be immutable. So first, how can we support immutability? Well, we allow you in your auto properties to not have setters. We can just have a getter only auto property here. But that prevents that, but it also, unfortunately, prevents initialization up here, and we really like object initializers. So we introduce the middle ground of initters, which are setters that they're only valid until the end of your object initialization. And then, so this is allowed, but this is not. Okay, good. We can now express objects that are immutable after construction. Awesome. But how do you mutate an immutable? How do you mutate it now, right? Okay, it's immutable, great. How do I mutate it? If I want to make this transformation, how do I do it? Well, you use non-destructive mutation, which is a common pattern that is, and you can express it without any language features, where you go up to, you essentially, but it's very arduous, right? If you look at the LINQ compiler, it uses non-destructive mutation all over the place, but before what I'm about to show you, so it has with methods all over the place. So there'll be like a public method in there that's public person with last name, string name, string last name, and then, it'll return you another person that's like the one you called it on, but with the last name changed. Copy and replace a few things. That's, writing all that out is no fun. So we made a language feature for it instead. Essentially, what we say is this: if you want to be value-based, if you want your things to represent values and not objects, mutable state, if you want them to be information and not substance in a way, well, you can now get all the right defaults generated for you by calling them records. So you can annotate these classes as being record classes, and there's also record structs. And now all the defaults change, and they're values by default. They have value-based equality. They even have a nice value-based toString, but they also support non-destructive mutation. Okay, so I said they had a nice toString, so I'm just going to delete some code here to make use of that. Just get rid of the render here completely. So what does non-destructive mutation look like on a record? Well, the way it works is that I can walk up to, let's say, so I want to create a new, another Mads value. Let's call it old Mads from back when he was Nielsen. I'm creating a record of the past. I can say Mads with, and then an object initializer, like that. So that's what records support that's new. And that means I get a Mads that's exactly like the one I'm calling it on, except that the last name has changed. And bear in mind that this is like, I'm only looking at Mads statically typed here as a person, but Mads was really a student, right? And with works with that. It actually creates another student and copies over all the student-specific data as well. It's not like you're just generating the copy this, copy that in place here. There's some virtual functionality inside of the records that we generate for you that takes care of that. And the same goes for equality. If I write line whether old Mads with the last name changed back to Torgersen. Now it would be pretty embarrassing if I can't spell that, but no one else in the world can. So, is that equal to Mads? Well, if you think about it in an object-oriented way, it shouldn't be, because they're two different objects. But value-based equality has been implemented in the records so that they should be equal. So just this once, let's actually run the code that I have on the screen. And we should see, I don't know why this takes so long, probably some AI thing. And not only do I have a beautiful toString, but I also have true, like they're compared as values. And that again, that actually implementing value-based equality on an object hierarchy is super hard, like, because they can be different types, and how do you make sure to compare the things you can't see statically and da-da-da. We do it for you. You never have to make those bugs again. So we really leaned into having like a full, records are really like value semantics as fully as we can possibly implement them. Thus kind of letting you do the immutable thing, the value-based thing that you would be the default mode of programming in a pure functional style. Okay, so I think I'm going to stop there. That takes us through most of the major functional influences on C#. Of course, we're not done yet. People who were at my talk yesterday will know that we're tinkering with unions now and seeing what we can scavenge from there. But this is a good place to get off the train. And I just want to say something at the end that I hoped I would have time for, and I do, which is all of this doesn't mean that C# is a functional programming language now. It's an object-oriented programming language at heart. That's still kind of the default, and that's still the grain, right? So you're not getting a full functional programming experience in C#, and you're never going to get that. Go and try a functional programming language if you want that, and you'll feel how things are still different when all of these things are the default, right? When you have to bend over backwards to have mutable state and to it's not actually that hard in F# because it's a beautiful language that integrates as much object-oriented programming as we do functional programming. But so just to give these languages their due, like the pure experience is mind-boggling and cool. And if you go and program in an actual functional programming language and come back to C#, if you ever want to come back, but I hope you do, but kind of hope you don't also, I don't know. F# is really cool. You might be a better C# programmer for it. Right? So this is not to say, oh, we've absorbed the functional paradigm. We've absorbed a lot of things from it, but the pure thing is out there, and it's really cool to try it too. Maybe if you do, you come up with another feature that would be really cool in C#, and you come and tell us, and we can steal that one as well. Okay, so that's it. Thank you very much.